Welcome to the fourth lesson of our unit on matrices. We are going to get started. First, the motivation for this lesson. We are going to be computing the inverse of a matrix, and you might be wondering why. So we've already determined that we can add, subtract, and multiply matrices, but we can't divide them. However, we can use the inverse of a matrix to overcome this obstacle, and through multiplication, accomplish division. So that's very much like saying, instead of 8 divided by 5, or 8 divided by 5, we're going to instead do 8 times 1/5. And so we're going to end up using the inverse of a matrix for division. So that is a good opportunity to discuss what is the inverse of a number. Obviously, unfortunately, as a video, we can't discuss this with a classmate, but I want you to pause for a moment, give yourself 30 seconds to a minute to think about what is the inverse of a number. So we can think of two types of inverses in math. One type of inverse is additive. The other type is multiplicative. So the additive inverse of a number is simply its opposite. So 5 would turn into -5. And note that the sum 5 plus -5 is equal to 0. Likewise, the additive inverse of -4 is +4. And when we add -4 plus 4, we get 0. But since we want to get something that will work like division, we need to think in terms of multiplication. So the multiplicative inverse is the reciprocal of a number. And when we multiply 5 times 1/5, we get 1. The inverse, the multiplicative inverse of -4 is -1/4. And when we multiply -4 times -1/4, we get +1. The multiplicative inverse of 1/2 is 2/1, or just 2. And 1/2 times 2 is also equal to 1. So whenever we multiply a number by its multiplicative inverse, we get the identity, the multiplicative identity, which is 1. We could think of the additive identity. So the additive identity is 0 because any number x plus 0 is still equal. I shouldn't be writing 0. Any number plus 0 is still equal to itself. So it remains unchanged. Likewise, the multiplicative identity is 1 because x times 1 is still not 1, but x. So to kind of summarize what this all means, the multiplicative identity for real numbers. So 1 is the multiplicative identity. So if x is not 0, then 1 times x equals x times 1 is equal to x. So for every non-zero real number, there is a number that we call x inverse. Notice that it has this exponent -1, such that x times x inverse is equal to x inverse times x1, or x, the original, such that the product, excuse me, is always equal to 1. This number is often called the reciprocal of x. And so the question is there a multiplicative identity for matrices? And the answer is yes, there is. So this, I'm pretty sure, can go away. We're not going to take time to predict. I encourage you to make a prediction regardless. So matrices do have a multiplicative identity, which we call the identity matrix. So again, pause, make a prediction. What do you think this is going to look like? And then when you resume, we'll just scroll down and look at the identity matrix. So the identity matrix can have many sizes. So a 1 by 1 is just the number 1. A 2 by 2 is going to be 1, 0, 0, 1. If we have a 3 by 3, it's going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. Pause for a moment and predict what the 4 by 4 identity matrix is going to be. So we have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And this is our 4 by 4 identity matrix. So in reality, it's really the identity matrices, plural, because we have one for every square size of matrix. Also notice that all of these matrices are in reduced row echelon form. So we have that staircase patterns with 1s and 0s, with the 1s on that main diagonal from top left to bottom right, and all other numbers being 0. So reduced row echelon form. Good thing to remind ourselves. What that looks like. So a fact is that if A is any matrix, then A times the identity matrix equals the identity matrix times A equals A. So the identity matrix is always square, but it can be made as big or as small as we need it to be. Two things that we need to briefly discuss. So first, notice that the identity matrix is associative. So associative. In general, for a matrix A times A and B, AB is not going to be equal to BA, generally speaking. There are certainly cases where this is true, but more often than not, in terms of the matrices we will encounter, this is not going to be the case. But the identity is especially special because it is associative. You might be wondering, what happens if we have a non-square matrix? So let's say that I have 1, 2, 8, 3, -1, 5. This has 3 rows, so it's a 3 by 2 matrix. The identity matrix I'm going to use is going to be the 2 by 2 matrix. So 1, 0, 0, 1. The reason why is because when we write our sizes, notice that the middles are both 2. And so our product is going to be a 3 by 2 matrix. And notice that 3 by 2 is precisely the size that we started with. So we can multiply this out. I encourage you to pause the video and practice. I'm going to shift this around a bit. So we have 1, 2, 8, 3, -1, 5. And then our identity matrix gets moved up. So we have 1, 0, 0, 1. Let me do the answer or the product in blue. So remember, we go inwards from both of them. So we have 1 times 1 plus 2 times 0. So for this first coordinate, it's just 1 times 1. On the next column, we have 1 times 0, 2 times 1, which is 2. And so you'll notice that all of the numbers in the first column, when we're multiplying the first column, will be times 1, and the second column will be times 0. So we'll get 8 times 1 plus 3 times 0, -1 times 1 plus 5 times 0. The second factors, because they are multiplied with 0, cancel out. And similarly, we have 8 times 0, 3 times 1, and then -1 times 0 plus 1 time or 5 times 1. So we do still get the matrix that we started with by appropriately picking the identity matrix. So even though the identity matrix is always square, it still works for matrices of any size. This is where we're going to end this first video. In our next video, we'll start looking at how do we use the idea of the identity matrix to construct the inverse of a matrix.